heat about 5 gallon, or you could heat about a gallon of water by 100 over 100 degrees Celsius, which is insane. It's about, I mean, 100 degrees Celsius, that's all the way from freezing to boiling. So if you could somehow set this Cliff Bar on fire and put it under a tank with a gallon of ice cold water in it, you could actually vaporize the whole thing just with the energy from this Cliff Bar.
Wow.
And if you think about the recommended caloric intake for an adult, it's something like 2,000 calories. That's 8 times as much. You could actually vaporize get the amount of food you eat each day contains enough energy to vaporize 8 gallons of ice.
That's amazing.
And how do you think they went about measuring this? The Cliff Bar Corporation, or whoever makes this. How do you think they know this has 260 calories of energy in it?
Burn it.
That is really the only way to do it. You have a device like this, and it's thermically sealed, and you put your food or your chemical, whatever, it's in the middle there, and you detonate it, and then you measure the temperature of the water in the hermetically sealed proof area around it. That's really the only way to do it objectively. But there's a problem in that this tells us how much chemical energy is in the whatever substance we put in the chamber. But that doesn't necessarily tell us how much energy is there that's available for human usage. Because if you think about it, we could put some gasoline in there and burn it, and we'd have a ton of heat released. But if you drank the gasoline, besides becoming very sick, you would not be able to produce any energy from it at all. So what we really want is a way of measuring the caloric value of materials in a way specific to living organisms, just how much could be released through chemical processes. So what we really need is something like this. Where we have, instead of a fire or a bomb, we have a living organism, which is a bioenergetic device. It's converting the chemical energy into thermal energy through its bioenergetic facilities. And the only difference here is that instead of boiling water, we're melting ice. So presumably we'd have 2 of these. We first have to measure how much ice is melting without the mouse. Then we'd add the mouse and see how much extra ice the mouse melts. And then we'd have a third one of these where we had a mouse that was given a piece of cheese. And then we'd measure how much extra ice was melted by the mouse eating the cheese compared by the mouse not eating the cheese. And that would tell us how much how much energy is in the cheese that is available to the mouse for energy. And of course, if we scaled this up to the size for a human, it would be something like this. I don't know if this volunteers instructed. I hope it isn't, but we've gone back here and trying to heat water. But you'll notice something else about, I don't want to stay on these calorimeters for too long. I just want to flesh out the issues that we're talking about when we talk about bioenergetic use of energy. In addition here to measuring how much water was heated, we also are measuring, we have oxygen going in and out, obviously, so the bioenergetic human can breathe, but the breathing really is crucial for the extraction of the energy from foodstuffs, just like it is for the bomb calorimeter. we also had some O2 in the chamber there because to burn anything, you need oxygen. And that is also true for bioenergetic creatures. We need oxygen for the most part to extract energy from foodstuffs. So another way to measure how much energy we're able to extract from foodstuffs is to measure, if you see all those test tubes at the bottom with the H2SO4, we're measuring how much less oxygen is in the air going out than there was in the air going in. And that tells us how much oxygen was used burning the foodstuff. So we have two of these, one with a guy who wasn't eating a Cliff Bar and the other with the guy who is. And we'd see how much additional oxygen was used with the guy eating the Cliff Bar. And that would tell us how much readily available energy for burning in a bioenergetic device. Now, I want to start moving away from these calorimeters because I don't think this is how food companies actually assess how much energy is in a candy bar or any other food stuff. I suspect there's some laboratory that tests this on bulk ingredients and they just sell lists of how much energy is in oats or honey or things like that, and they just sell it to the retailers or the manufacturers, just give an estimate. So if you notice, this flavor, peanut butter banana, has exactly 260 calories, where if you get the regular chocolate chip flavor, it's exactly 250. I don't think they measured either one. And besides, how much energy you get from any food item has a lot to do with who you are, how large you are, what temperature in the room is, and even things like what kind of mood you're in, or if you've been sick lately, which is going to affect the enzymes in your stomach. So none of these numbers are really that exact. But insofar as anyone uses calorimeters at all, they're going towards measuring how much oxygen is being used, not towards how much your body is actually melting water or heating water or melting ice. So these types of devices that measure oxygen intake are used at least in exercise physiology laboratories. And what we're really interested in is how much oxygen you're using and how much oxygen you're capable of using. So when you're at rest, you're using a lot less oxygen than when you're running on a treadmill or doing something very strenuous because you require more energy per unit of time. So you need to extract more energy from whatever fuel you have stored in your body. And exercise physiologists call this VO2, which is the velocity of atmospheric oxygen in your body. The more strenuous the exercise you're engaged in, the greater your VO2. And in particular, they want to know what your VO2 is relative to your potential. So
What's VO2 mean again?
velocity of oxygen. O2 is atmospheric oxygen,
Okay.
free floating oxygen, not oxygen as it is used in organic compounds.
Okay.
It's just, the oxygen in the air. And you're constantly breathing it in, breathing it out. So it runs through your body at a certain speed. That's the velocity of oxygen.
Okay.
When people like this, when you're exercising, that velocity goes up a lot. But what we're particularly interested in is how fast the velocity of oxygen is relative to your potential. So these people look like they're in pretty good shape. So they could probably do quite a lot of work in terms of speed or weights they're lifting or distances they're covering without really breathing very hard. So their velocity of oxygen would be at a relatively low level of their potential, whereas someone who is out of shape would be breathing a lot harder, would be a lot closer to 100% of his potential. And this is what exercise physiologists call VO2 max, which is the maximum velocity of oxygen you're capable of. And these are really the important concepts that we need to understand to move on to the rest of this presentation. So we're not going to talk so much about Cliff Bars and watt hours and calorimeters, but it's good to understand where all this comes from. So we extract energy from food we eat. What types of foods do we extract energy from? What are known as the three major food groups. Anybody know these?
Carbohydrates and fat.
Yep, Rachel's got it. Carbohydrates, which includes sugars and starches, lipids, which includes fat and oil, and protein.
Proteins.
And from these food groups, we extract energy, but we also use some of them for structural purposes, which means our body is actually made out of some of these things. So carbohydrates, none of our body is actually made out of carbohydrates. We eat carbohydrates for the energy value they provide us. And when it comes to lipids, actually, part of our body is made out of lipids. So you need fat because partially you're actually made out of fat. In particular, cell membranes, I believe, are mostly made out of fat, as well as the organelle membranes. Other certain hormones are also made out of carbohydrates. So fats are not all bad. In fact, certain fats are essential. Certain fats your body will synthesize. So even if you eat a no-fat diet, your body will make fat out of other stuff. And there's certain fats you absolutely need to eat or you will be malnourished. But for our purposes, we're looking at the energy properties of fat. Fats contain tons of energy, a lot more energy than carbs. But we'll get back to that later. Now, I really don't want to talk about protein very much. I just mentioned it here to be complete. Protein, we ingest protein. We use protein mainly for structural purposes. For the most part, we are made of protein, and particularly our muscles. Most of the bulk of our body that's not water is protein. And we can derive some energy from protein, but I'd rather not talk about that because that's a whole other topic. Any questions about that before we really get into it? So we know that we need fuel from food sources to power our body. And we know we need oxygen. We know we get it from the foodstuffs, different kinds of foodstuffs. But how is that energy delivered from our digestive system to all the cells where it's going to be used? And a helpful way to think about it is to first think about how a power station in a city gets fuel, like coal or oil or nuclear or hydroelectric or solar, whatever it may be, converts it into electricity, which is what we want to use, and then delivers it to houses, farms, apartment buildings, factories, where it's actually used. So it's all the conversion has been done in the central power station. So if you're in the house or the farm or the factory, all you need to do is plug your device into the wall socket and hey, presto, it works. And this is good to think about because to understand how bioenergetics works in the human body, you have to understand that this is not how the human body delivers energy. The way the human body delivers energy to its cells is something more like this. So imagine that in your house, you have your refrigerator and your air conditioner and your computer and all the other devices, your space heater, all the devices you want to power by electricity. And imagine that you have no electric outlets at all in your house because you are a bioenergetic device and not an urban power grid. So instead of getting electricity from a wall socket, a truck like this pulls up in front of your house 3 times a day, just after mealtime, and delivers all this broken down pieces of coal. So the digestive system it has extracted the coal from the slag, and it has broken the coal down into little bite-sized pieces. But you need it in the form of electricity. So it is your responsibility as the end user at your urban residence to have a little furnace in your basement or in your front yard or in your closet where you burn the coal and then convert it to electricity. And then you are responsible for getting that electricity to your devices. So where are the dishes up? So if you can see this device here, this is a 40-volt lithium ion battery that I use to power a lot of my power tools. It's very nice. It's modular. So you just click it, you put it in your hedge trimmer, you trim your hedge, you take it out, you click it, you put it in your leaf blower, you blow some leaves, then you stick it in the charger and recharge it. Now imagine if all the appliances in your house worked on a modular lithium ion battery like this. So when you wanted to run your refrigerator or your computer, you couldn't plug it into the wall socket. You had to stick your lithium ion battery into it. And when it was depleted, you'd have to recharge it in your coal furnace. Because all you get from the power company is deliveries of coal. You are responsible for converting it into a modular unit. So if you can get your head around that analogy, that the digestive system just delivers the fuel in little bite-sized pieces to the cell, and the cell is responsible for converting it into packets of usable energy. What is the bioenergetic analog of the lithium-ion battery?
Blood energy from the cell.
What is the little packet in your cell that performs the function of the lithium ion battery and actually gets plugged in? Things, if a muscle needs to contract, or if an electrolyte pump needs to pump electrolytes across a cell membrane, or a neuron needs to send an electrical signal, anything in the human body that needs energy. At the point of application, we can't use starch or fat or any of those nutritional.
ATP?
Rachel's got it. ATP.
Did you teach this class?
The mechanism of the mechanism of energy contained within each cell, that the substance is almost always adenosine triphosphate, abbreviated ATP. So adenosine triphosphate is this little organic molecule, looks something like this. And that is the molecule that powers everything in our body that uses energy. We get the energy from food, but we don't use it in food form. We don't have little pieces of sugar or fat floating around the cell powering things. Everything in the cell that's powered is in the form of ATP. So the food is sort of like the coal reaching the cell, and the use of the energy is in the form of ATP, which is like the lithium ion battery. So the cell is responsible for extracting, breaking apart all energy in molecules is in the connections between the ions. So it is the cell's responsibility to break apart the energy containing bonds in the sugar and fat, and then store it in the ATP. And then the ATP floats around and gets used. And the place, so I was hoping Morris would be here because he has actually passed a course in organic chemistry, which is really what separates the real scientists from the phonies. I took inorganic chemistry in college and found it very difficult, so I never got around to taking the organic chemistry course. So I don't want to talk about the nuts and bolts too much, but the part of the ATP that contains the energy that we use is this third, so that ATP, it's this, the most of it is this adenosine, and then it's got this string of three phosphates. A phosphate is a phosphorus ion surrounded by oxygen ions, and it's the bond, all bonds between ions contain energy, but for some reason, the usable energy, the readily extractable and reusable energy is in that third bond between the last two phosphates. So what the cell has to do is get the energy out of the food, store it in that third bond, and then that that adenosine triphosphate is ready to go plug into a muscle to make it extract, or plug in to an electric light pump to make it pump, or anything else it needs to do. Once it does that, what happens basically at the point of application, that third phosphate pops off. It's then reduced to being adenosine diphosphate, because now it only has two phosphates, ADP. I don't know if the company ADP named themselves, but I have no idea.
We use 80 people too.
Yeah. But this, yeah, that's what you have. And then once the ATP is converted to ADP, it's useless. And your cell has to find some way to rephosphorylize it by attaching that third phosphate back on. But to do that requires energy derived from more food sources. Any questions about ATP so far?
ADP, automated data processing, or automated dietary processing?
Yeah, I knew there must be some other reason for the choice of that name. So within the cell, there are four ways ADP can be converted to ATP, and we're going to list them in order of how fast they work and in how much energy they yield. So the fastest but lowest energy yielding process is immediate energy. So immediate energy, we'll go into more detail about all these. Immediate energy is basically the ATP that's already there, and also the creatine phosphate, which rephosphorylizes ADP pretty much instantaneously. Going down the list, the next fastest process, which yields slightly more energy, is non-oxidative glycolysis. Don't be scared by the name. Non-oxidative just means no oxygen is involved. Glycolysis just means the breakdown of glucose. So basically, this is the partial burning of sugar. You take sugar, but you don't burn it because you don't have oxygen. You just sort of fake burn it. So you get a little bit of energy from it, but not as much as you would if you really burned it. So think of like a fire that you light the fire, but then throw a blanket over it. So like it's sort of like how charcoal is produced, I guess, at the cellular level. Then the next fastest process, which yields even more energy, is oxidative glycolysis, which is just the complete burning of the sugar molecule. And last and slowest, but by far the highest yielder of energy, is the metabolism of lipids, which is to say the burning of fat cells. Fat cells contain a lot of energy, but they burn very slowly. And just going to show you some one slide equations. Immediate energy is ATP or ADP combining with creatine phosphate in the presence of a single enzyme present in all cells, creatine kinase, which yields ATP almost instantaneously. So if you've heard anybody ever taking creatine as a nutritional supplement, that's why they take it. Just the idea that the more creatine you have in your cells, the faster you can rephosphorylize ADP without the need. Really, not only do you not need oxygen, you don't even need food to do this. You just need creatine, which is stored in your cells at all times. But that only yields you one molecule of ATP per reaction. moving down the list to non-oxidative glycolysis, we have a molecule of glucose, we have rapid glycolysis, we get two molecules of ATP here. So this is twice as high an energy yielding process. The lactate is really just the partially burned glucose. So the lactate can later be burned and have more energy extracted from it, but that's more time consuming and requires oxygen. The oxidative glycolysis, we take the glucose or the lactate or pyruvate, which is a related substance. And here we need oxygen. And this oxidative catabolism is actually a very complicated process involving the Krebs cycle and the electron transfer process, which is something I never completely understood, but it's a very long and slow process. But it yields 36 molecules of ATP, which is an order of magnitude more than the other processes we've looked at. And it also releases carbon dioxide and water as byproducts. And then the last and slowest process, oxidative lipolysis, which is the burning of lipids, burning of fats and oils. And this, I don't know if all lipolysis yields 129 molecules of ATP. This is an example they have in the book involving palmitate, not some kind of oil. From the name, it might be palm oil. But fat molecules, they burn slow, but they yield 5 or 10 times as much energy as sugar or as anything else. Now that we know about all the different processes and we know their order in terms of usage, I want to put some numbers just to show you just how big the differences are in terms of speed and yield of energy. So what this table does is it lists for the first 3 processes we talked about, the immediate energy source, the non-oxidative glycolysis, and the oxidative glycolysis. So we're ignoring lipids for the moment. In the column on the right, the authors of the book have estimated how much energy in kilocalories they think is available in your body at any given time. Now, obviously, these are rough estimates since people differ greatly in size, and obviously some people have a lot more energy stored than others, and even the same person at different times of the day is going to have different amounts of energy stored. But they estimate that in immediate energy sources, you probably on average have about 11.1 kilocalories of energy in ready immediate sources in your cell. Now, that's not a lot of energy. Consider that a Cliff Bar is 260 calories. Even the regular chocolate chip flavor is 250. So this is not even a tenth of a Cliff Bar. But it's the advantage is it's there immediately. And so it can be delivered at a very fast rate. They estimate the rate that it can be delivered at as 36 kilocalories a minute. So if you do something super strenuous and you need energy delivered at that rate, you're not even going to have enough kilocalories to go for more than 20 seconds before you run out. So doing the equation there, I compute 18.5 seconds that you have if you're going all out, applying all of your immediate energy sources. Now, has anyone here ever been on a track team?
Mm-mm.
Anyone here a fan of track and field events? Well, you might have seen, okay. This is typical, this 18.5 seconds, this is typical of events like the 100-meter dash, because these are events where people are just running as fast as they possibly can until they're on the verge of collapse when they get to the end of 100 meters. And typically these events take about 20 seconds. That's why 100 meters was chosen as the sprint event. I mean, if you're on a track team and you're running 100 meters at a lot more than 20 seconds, your coach is just not going to believe that you're really trying. Whereas I don't know what the world record is for 100 meters. I assume it's below 18.5 seconds. I don't know how much faster it is, but this is typically, or things like lifting a very heavy weight. If you're watching a weightlifter finish a very heavy lift, if he's struggling with that weight for more than 10, 15 seconds, his coach is going to tell him just drop it. If you didn't finish it in 15, 18 seconds, no way you're going to finish it, because something like that requires energy at such a high power output that if you can't do it with immediate energy sources, you can't do it at all. Moving down to non-oxidative glycolysis, the amount of energy you have available to you is slightly larger. It's 15 kilocalories. And remember, when you're using the lower and the slower energy source, you have access to the faster one too. So that if you're doing, okay, I'll give the example. Doing something slower using non-oxidative energy sources, you have a little more energy available to you, but you have a much slower rate of delivery. They estimate 16 kilocalories a minute. That's less than half the speed. So if you want to do something at a steady rate of output that lasts for more than 18.5 seconds, you better slow down to less than half the speed you were before, and you now get an extra 15 kilocalories of energy if you maintain a speed that's half as slow. And doing the math here, you get almost a whole minute, which if you were on a track team, you'd say, oh yeah, that's like the 200 meter or 400 meter race. So that's a race that cannot be run at your top speed, because you're going to run out of immediate energy sources. So you'd run it at a slower speed, but you'd get more energy available to you. And again, if you're running a mid-distance race at more than 60 seconds, your coach is going to think you're not trying very hard, or maybe you have an injury or something, because you should have, going all out for non-oxidative glycolysis, you should have almost a minute at your top speed from that energy source. Now, once we slow down more than that to about 10 kilocalories a minute, then we have 2 orders of magnitude more of ready energy resources. They estimate 2,000 kilocalories total, which can be delivered at speeds of up to 10 kilocalories a minute, which, if you do the math, is over 3 hours. So this is like something like a marathon. You can just keep running for hours. And if you think about it, if I'm running at a speed that I can maintain for 3 hours, someone can just hand me a bottle of Gatorade, which has glucose in it. I can drink the Gatorade. I can run all day. I mean, as long as I keep drinking Gatorade, I can run for several. I mean, at some point, I'm going to collapse for nervous exhaustion, but I will never run out of energy. That 3-hour limit, that's assuming I don't ingest any additional food. But if I keep, I mean, if you look at some of those Ironman events, they go on for 3 days. And as long as you keep eating or drinking something with sugar in it, there's really no bioenergetic limit to how long you can keep powering yourself at that, as long as you don't try to use power at a higher rate than that. Now, what about lipids? Let's try to make this kind of estimate for lipids. So those of you who have done much, someone have a question? Those of you who've done much hiking or camping might have heard of the rule of threes. Sometimes the rule of fours, but it's just a rough estimate. You can go 3 minutes without air, 3 days without water, 3 weeks without food. And some people would substitute 4 for 3, but let's just leave it at 3. So if you can go 3 weeks without food, we just said you could go 3 hours and 20 minutes. And yet the survivalists are saying you can go 3 weeks. Well, they're obviously not talking about glucose. They're talking about lipids. And later in Brooks and Fahey, they give these estimates. So the 2000 is the number we already saw here, 2000 for oxidative glycolysis. And they state that again here. And then they have an estimate for lipids. And specifically lipids stored in adipose tissue, which is fat cells, because your body stores a lot of fat. It doesn't store, we don't have carb cells, we have fat cells. The fat cells store fat, and your body will build if you eat a lot of fat or if you eat a lot of carbs and you have excess carbs that are converted to fat, your body will build additional fat cells to store the body likes to hold on to fat precisely because it can be used for so long. There's really only two types of tissue in your body that store carbs. Anyone know what they are? Actually, they're on the page here. Muscle and liver. And building muscle is hard, as anyone who's tried knows. Enlarging your liver. I don't know if you want to do that, but building additional fat is very easy, all too easy. And the authors estimate that the typical amount of fat energy you have in your fat cells is 141,000 kilocalories. I mean, that's 2 orders of magnitude more than you have stored carbohydrates on average. That is why survivalists say you can go 3 or even 4 weeks without food because of the energy stored in your fat cells. And if we go back to this equation, we take the 141,000 calories and we solve for X being the rate of power delivery over a 3-week period. So I just converted the 3 weeks to minutes and then solved for X. We get a power rate of 4.66 kilocalories per minute, which is less than half the speed of energy delivered by glycolysis. So you can last for 3 weeks without eating, powering yourself on fat, as long as you don't do anything more strenuous that would take more than 4.5 kilocalories a minute. And this is really getting down to what I really want to say in this presentation, which is this graph. This is a graph which I think is the most important graph in the entire book to me. And this graph brings together all of the things we've talked about: VO2 max, energy derived from sugar, energy derived from fat. And what we're graphing here is the 3 bars, the 3 columns are energy used at different rates of exercise. So the 25 means this is a person engaging in activity which only requires 25% of his maximum oxygen velocity. So this is a relatively restful situation. The 65% you're doing something that requires you to pump oxygen through your lungs at about 2/3 of your cardiovascular capacity. So you're breathing pretty hard. You're doing something that requires you to produce a lot of energy rapidly. And the 85%, you're going almost all out. And the y-axis here is the amount of energy you're using. So not surprisingly, the columns are a lot higher as you're exercising harder. You're needing, so the y-axis is measured in kilocalories per minute. You're using much higher rates of output at the higher VO2 levels. And then the different colors in the bars are the source of the energy. So what I really want you to pay attention to is the white. The white is muscle glycogen. This is carbohydrates being released from your muscles, because your muscles are the primary source of stored carbohydrate. And then the gray bars, the light and dark gray, that is lipids. Muscle triglycerides and plasma free fatty acids. So those are all lipids. And then the black at the bottom is plasma glucose, which is blood sugar. So the thing to see here is when at 25% of VO2 max, you're just sitting there looking out the window. You're using less than 100 kilocalories a minute. And most of that energy is coming from free fatty acids, lipids. Only a very small amount of it at the very bottom is coming from blood sugar. So sitting there looking out of the window, you're burning fat. You don't have to exercise to burn fat. You're burning fat just sitting there doing nothing. 25% VO2 max. That's just normal sort of idling level bodily functions. Now you start exercising hard, you're using a lot more energy. But where is that energy coming from? Where is that extra energy coming from to power that more strenuous exercise? In the 65% column, well, some of it is coming from muscle triglycerides, which is fat stored in your muscle, but at least half of it is coming from muscle glycogen. So when you are exercising harder, you're burning a little bit more fat, but you're burning a lot more carbs. And that shouldn't be surprising since carbs burn at a much faster rate. When we need energy rapidly, delivered at a rapid power output, we really very limited in how much we can use lipids. And when we go to 85% of VO2 max, look at the size of that white rectangle in the 85% column. I mean, we are just burning through those stored carbs. And remember, we don't store a whole lot of carbs anyway. 2,000 kilocalories of carbs versus 141,000 of fat. So the harder you exercise, the more glucose, the more sugar you're burning, and the faster you're going to run out of it. Whereas you're not really burning much extra fat at all. And when I saw this graph, I just stared at it and I thought the whole exercising world is exercising because they think they're burning fat, but you're actually not burning much more fat than you would if you were just reading a book. And the yeah.
Accountants everywhere rejoice. One week.
I understand. You just sit back down. You don't need to look at
So if the reason you're exercising is to burn fat, you might as well not. But I'm not saying you shouldn't exercise. I think there are some very good advantages to exercising, and you'll get those advantages from exercise, whether you understand it or not. But the better you understand it, the better you can design your exercise program. So if I have a few minutes left, just talk about what I think the benefits of exercise are. So carbohydrates can be metabolized as energy. We saw that. Lipids can be metabolized as energy. Excess lipids can be stored in adipose tissue. Excess carbohydrates can be stored in adipose tissue as lipids. Now, the idea that you're burning fat in exercise, I think if you understand how slow fat burns, you'll understand that isn't really workable. But I think what I assumed before I read this book is that, well, maybe you can't use the fat during exercise, but just like you converted the carbs to lipids, you can convert the lipids back to carbs, right? And just reverse the process. It turns out you can't. I mean, there may be some other organism that can, but I don't think human beings can. And they don't say so specifically in the book. They have hundreds of pages showing all kinds of processes. And all I can say is I couldn't find anything showing a process for converting lipids to carbs. You can convert carbs to lipids and you can burn lipids to produce energy, but you can't produce the carb from the lipids. So you can't, not only can you not burn the fat during exercise, you can't convert it to carbs to burn the carbs either. What the body converts, what gets stored as fat stays fat and can only be burned as fat. And this is just another graph from the book showing basically the same thing, that as this is hypothesized. The other experiment they had was really interesting because they actually had radioactive isotopes of carbs and lipids, and they were able to track them through the body to see. That's how they know how much of the energy you were producing at rates of exercise came from different sources. This is just an idealized situation as they see it, showing as your VO2 increases from rest to 100% all out exercise, the solid line shows the percentage of energy derived from fat, and the dashed line is the percentage of energy derived from carbohydrates. And not surprisingly, as you exercise harder, you're deriving more energy from carbs and less proportionally from fat. Now, the amount of energy you're deriving from fat in terms of calories per minute isn't actually going down. It's probably staying constant or even rising slightly, but this is proportional. It's going down a lot. And they pinpoint this point, they estimate at about 2/3. If you're going at 2/3 of your capacity of oxygen usage, they think you're switching from being mostly carb using, mostly fat using to mostly carb. And the last thing I wanted to bring up, I don't have a slide for this. The one word I didn't mention somehow in the last 55 minutes is mitochondria.
Yeah.
Mitochondria, I almost talked about this when I said, imagine you had a furnace in your closet where you had to put coal in the furnace to charge up your lithium ion batteries. The mitochondria is the furnace in the cell that converts the sugar. It's where you literally burn the sugar and the fat to produce the energy and the ATP. And it turns out that just like you can build bigger muscles by lifting heavy weights, you can actually build bigger mitochondria by doing things that require lots of energy delivered rapidly. And the arrow, the rightward pointing arrow they have there that says training, basically the more trained you are, the bigger your mitochondria get and the more sugar and lipids they can burn per minute. So you sort of shift that crossover point rightwards. So the 65% thing stays constant no matter how well trained you are, but the actual amount of energy you can produce increases because you can actually generate more energy. So for someone who's very out of shape, going up a flight of stairs is probably 100% VO2 max, whereas someone in reasonably good shape, it's maybe only 40% of VO2 max. So the better shape you're in, the more of your activity you can power using fat because it's not requiring you to kick in higher levels of VO2 max because you just have more mitochondria available. So there's a lot more even at lower levels of VO2 max. And that is really one of the principal advantages of exercise. First of all, building muscle increases the storage of glycogen. I always give the example, someone who's very seriously overweight is going to have trouble getting up a flight of stairs and is going to be very tired at the top of the flight of stairs. And people are going to say, well, if they're being mean, they might say, that guy has all that stored energy in his fat. Why is it so hard for him to climb the flight of stairs? Well, because he can't use the fat, because it's such the problem isn't that he has a lot of fat. The problem is that his mitochondria is very shriveled up. So he can't really burn a lot. So in order to get up a flight of stairs, he has to burn through all of his stored glucose. So when he gets to the top of the flight of stairs, not only is he out of breath and exhausted, but he's hungry. And you say, but what about all that fat? He can't use the fat because the fat burns too slowly. Unless he's gonna take 2 hours climbing the flight of stairs, he needs rapid energy production. So either he needs to store more sugar or he needs better mitochondria. And exercise helps you do both of those things because bigger muscles are not just for looking good at the beach. They're also for storing glycogen. And cardio fitness means, okay, I also say allows for increased storage of protein. I purposely avoided protein, but protein is also important. And muscle is actually made of protein. It's almost pure protein. So that's a good thing to have too. And really what we're talking about is that exercise increases mitochondrial density, the total proportion of the cell that's mitochondria, which allows for greater lipid oxidation at a given level of oxygen usage. So it shifts this curve to the right, as we said. So you can actually do more with fat in the same amount of time. And you can do more and more strenuous exercise without having to bring the carbohydrates into it. And many other advantages which are not directly related to bioenergetics. And we're out of time and out of slides. And thank you everyone for being here in the office and at home and for making this happen.
Thank you.
Thank you, Ben.
Thank you, Ben.
Thank you, Ben.
Have a good day.
Thank you, Voter. I think that's it.
You guys tell everybody how to burn fat. Ketosis.
I didn't want to talk about that. It's an interesting topic, but I said at the beginning, I don't want to talk about protein.
Okay.
Yeah.
Well, that's surprisingly, they're not at all what I thought.
Yeah.
It's explanation about what happens when a fat person